Hi, everyone. I'm Dan Jones from the Sustainable Montpelier Coalition, and I'm here to welcome you tonight to the presentation from Roger Hill, Climate Change Comes to Vermont. The we who organized this event are the Sustainable Montpelier Coalition. We're a relatively new nonprofit formed to help our city adapt to the looming challenges like climate change. We're joined tonight in this effort with the Unitarian Church's Climate Action Team, and I'd like to ask the members of them if they could stand up for a second back there. I saw Harris was here somewhere. Yeah. Last week, I came across a copy of a speech given recently by Bill Moyers. Now, Moyers is one of my heroes. He's, I think, one of the most courageous journalists that we've had around for the last 50 years. And he was telling the story of another courageous journalist, Edward R. Murrow, during World War II. In September 1939, Europe was hours away from going up in flames. Yet, the powers at CBS in New York ordered Murrow to feature an entertainment broadcast, spotlighting dance music from nightclubs in London, Hamburg, and Paris. There's so much bad news out there in Europe, they said. We want some good news. Murrow in London snapped, wait a minute. This show is scheduled to be broadcast just as Germany is about to rape Poland? And we would like to call Europe Just Dances? Finally, Murrow decreed, oh, the hell with those bastards in New York. It may cost us our job, but we're going to tell the truth. And they defied the bosses and gave CBS the hottest story in the 20th century. Even after that, the network was reluctant to provide 5 minutes a day to just report on what was going on. And that is the same as our networks and cable stations are doing right now with the climate crisis. They're refusing to report it. Moyers in his speech continued by challenging the young reporters. Now, some of you will go to Washington to report this madness. And yes, I said madness. Of a US government that scorns reality as fake news, denies the truth of nature, and embraces a theocratic theology that welcomes catastrophe as a sign of the returning Messiah. It's madness, it's superstition, destruction and death. Can't we get this story right? Can't we tell it? Can't we connect the dots and inspire people with the possibility of change? We need to keep the whole picture in our heads, how melting ice sheets in the Arctic can create devastation in the Midwest, and connect the dots for our readers. And that, my friends, is why we're here tonight. We are here to help share the real news about what's happening in the climate crisis and how it's going to affect us here in Vermont. We need professional help and courage to understand what's going to happen. And for that need, we are graced tonight with Roger Hill, a man who needs basically no introduction to you as both a trusted radio weatherman and a strong point of view. And we know Roger will give us a straight story. He's also trusted, you know, by the Vermont utilities. He's basically tells the utilities where to position people when weather events are coming. Got into one conversation once where a guy who was in one of those crews said, we're trying to figure out how to bribe Roger so he might place us in some place that's more fun in the evening to wait. So this talk is going to take us out of our comfort zone and help us understand the truth and show what needs there are to take action and create a sustainable and durable city right here. The challenge might be in creating a small city that redesigns itself to meet the climate crisis and provide a secure future for its citizens. Civilizations define themselves on how they face adversity and come together to find a way through. Hopefully that spirit will engage us this evening. After Roger's talk and questions, we're going to come back and give you some ideas that Sustainable Montpelier believes need to be addressed. But we need your ideas, energy, and imagination to make anything happen. So to help your ideas and be expressed, you'll see each of you has been given a response card and pencils. After the presentations and questions, we ask you to fill these out and we'll collect them because we really want to know what you would like to be involved in. Also, we know that you have a lot of questions and will increasingly have questions as the presentation goes on tonight. So you have those 3x5 cards that were handed. At the end of the talk, we'll collect them and start asking them quickly, just to sort of save time and keep things moving. If there are more questions that we have time for, if you give us your email on those cards, we'll be happy to have Roger respond directly. But first, without further ado, might I introduce Roger Hill.
Well, thank you everyone for coming out. Quite a big crowd tonight. What I'm going to do is take you through some things that I've been noticing. And of course, I've been doing the meteorology for about over 40 years now. And I started out in the Army, and I've been around the country and worked for the National Weather Service. For the U.S. Army is where I was kind of trained in meteorology. And sort of trial by fire when I was in the Army, and even during the National Weather Service years that I was in, where I had to put out tornado warnings and work with hurricanes coming up the coast of Cape Hatteras and this kind of thing. So what interests me is the things that cause, unfortunately, you might say I'm a ghoul here, but what kind of causes destruction and what might cause property damage and of course fatalities. So I'm into weather hazards, if you will, and boy do we have weather hazards going on across the planet right now. And that's what this talk's going to be a little bit about, and maybe what the future projections are, and then kind of zeroing in here on the Green Mountain State especially, and also in the city of Montpelier, this particular area a little bit as well. Now I wasn't going to have this slide, Dan, but I did want to point out that the content is, my conclusions are drawn up as my life experience in meteorology. And I'm not a research guy, but I follow a lot of people's research. And if it wasn't for those researchers, I couldn't do what I'm doing, even in meteorology or trying to figure out what the climate's doing and how fast it's changing, et cetera, et cetera. But my main issue is to try to sort of connect the dots, if you will, between climate and weather. People think of climate as their wardrobe, and your weather is your day-to-day, is exactly what you're going to choose to wear on that particular day. So these go hand in hand, they're not exactly the same thing, so let's go. This presentation is going to be about some what we call global heating, or environmental destruction due to global heating. This is, of course, from greenhouse gases. The climate shift that's on, not always in winter. I'm going to throw some curveballs at you from the latest science. And the increasing trends, of course, in our extreme weather that we're seeing, as well as Vermont climate trends and projections. So is this a new normal? Increased evidence has linked extreme weather to the loss of the Arctic sea ice that occurs in fall and spring. And also, well, you lose the Arctic sea ice in the fall, but in spring we also have a quickening, a loss of snow cover. And that pervades much of Alaska and northern Canada and parts of Siberia and Scandinavia as well. So these are things we're watching right now. But it started with Francis Fabris, which is about 2012 paper by Jennifer Francis of Dr. Jennifer Francis of Rutgers, who connected up the loss of Arctic sea ice with changing weather patterns. And there's very much a link, and a body of research has been built upon this. It was very controversial to start out. There's some folks in the climate community that still argue with that, but they're becoming less and less, and there's a lot of good research all the way from China, Russia, all the way across Europe, and of course into North America and Japan. So CO2 levels the highest in 3 million years, and the Earth's temperature is responding, although not evenly around the globe. So this is the famous hockey stick that we have here that was developed by Michael Mann. And you can see that the planet was cooling. This is a year 1000, 12, 14. You can see along the line to 2000. And you see that we were kind of sort of cooling a little bit. And this is our part of our natural climate. The climate is going from glacial to interglacial. And we're coming out of the interglacial. In other words, the planet should be cooling right now. And it is, up until the time the Industrial Revolution started to kick up a lot of greenhouse gases in the form of carbon dioxide. So CO2 levels are the highest we've had now. This number here, 3 million, I have had to update that constantly. It was 850,000 about a year ago. And so we're really bypassing some milestones. Kind of gives you an idea of just how much carbon dioxide there is in the atmosphere. But the Earth's temperature is responding, although not evenly around the globe. May 2019 is the 412th consecutive month warmer than average, and it's consecutive. I don't think we're going to be looking back, period. So the last time, looking back a few 100,000 years, the last time the CO2 levels were this high, the globe was several degrees warmer, sea levels were tens of feet higher, and humans didn't exist. So this is where the CO2 is, but take a look at our Earth's temperature right now. Now, if we stop putting carbon dioxide in the atmosphere right now, we would still have to catch up all the way to 414 parts per million, I think is where we are as of today. And as the northern hemisphere greens up, it pulls that carbon out of the sky, out of the atmosphere, and so those numbers come down, but then they oscillate right back up as soon as the decay of leaves happen in the northern hemisphere. So there's this, technically this wiggle, they call it the Earth breathing. And a lot of this measurement is taken from the Mauna Loa research at 14,000 feet elevation in Hawaii, the Big Island. So present CO2 levels are way out of whack with temperature. Again, this is our deal here with the carbon dioxide. You can see the Earth's atmosphere sort of breathing as the northern hemisphere pulls that CO2 out and then releases it, but you see the natural trend. This is kind of where we are right now, looking sort of in a future projection. You can see 1960, this is projected to 2100. This is RCP 8.5, that's fossil fuel intensive. And unfortunately, that's the kind of trend we're on. So in one way you could look at this without laughing. Candidate A, candidate B, candidate C. So why are greenhouse gases such a big deal? Well, the atmosphere, starting with the sun, produces solar radiation. 10,000 degrees, when it hits the Earth, it warms it up to 60 degrees, but it really wouldn't warm it up to 60 degrees if we didn't have greenhouse gases. Everybody says, well, CO2 is either good or bad. What is it? Well, it's the sweet spot. We want the Goldilocks spot, which is approximately 280 parts per million. If it went below that, say we only had 100 parts per million of CO2, it would be freezing cold, nobody would exist. So there's this little kind of middle ground. And right now we're at 414 parts per million, and we're way out of whack, and that's going to raise the temperature. That's like a thermometer. So looking at the raw data versus the data that is smoothed out to get the trend, this is, ENSO is El Nino Southern Oscillation, and that's when El Nino is very strong in the Pacific. It radiates a lot of heat from the surface of the ocean. And when it's the other components of changing climate, kind of on a year-to-year basis, is volcanic. Remember Mount Pinatubo, it released a lot of stratospheric ejection material into the stratosphere, which then filtered the planet, and the temperature consequently dropped 2 degrees Celsius across the planet for a couple years and then gradually rose. Very temporary. The other component here is solar, and there's very minutia, but we have solar cycles. We're going into solar cycle 25 now from 24. We've had a very low sunspot minima. So the actual sun is putting out just a little bit less energy, and when that interacts with carbon dioxide and our greenhouse gases under normal circumstances, there's a little bit of a cooling effect. And we can see that that is a little bit of a player, but not like carbon dioxide or adding greenhouse gases is. All right, so this is 2018, the global temperature. This is the 4th hottest year on record. I want you to take a look at this a little bit. It's kind of interesting. And notice that North America is basically at near normal. In other words, it's not warming. There's this, what we call the North Atlantic, I forgot what it is now, North Atlantic warming hole. And it's like, why don't they just call it a cool blob in the Atlantic? Well, because the rest of the planet is warming up. It's not here. This has to do with some Greenland melt. Also, it has a lot to do with the ocean circulations, the thermohaline circulation, and what's going on with the Gulf Stream and where it goes underwater. And it's kind of hard to explain. but it has a lot to do with the salt in the water versus fresh water. And there seems to be a halt that's taking place, which is actually going to warm up the East Coast and make the North Atlantic a lot colder. That could have regional effects, of course, on Europe, maybe the northern part of the United States, maybe, who knows, even here in Vermont. Hottest years on record globally, the last 5, you can see that the temperature is going up, and the Earth is now hotter than at any time humans have been in existence. That's amazing. Now, in the past, we've had temperatures that were much hotter. The hottest temperature was the thermal, the Paleo-Eocene thermal maximum, and that's when the Earth warmed up to about 10 degrees Celsius to the point where it was just nothing. It was the 6th or 5th mass extinction, and unfortunately, we're kind of following in its shadow with the amount of carbon dioxide and greenhouse gases we're throwing up into the atmosphere, as if it's an open sewer. So evidence implicating humans, I want to explain the top and the bottom charts here real quickly. So if you had the computer modeling world and you ran just natural model temperatures here, you can see 1900 to 2000. This is what it would look like. But if you look at the observed temperature, it's anything but that. There's a lot of natural variation. We got cycles of ocean warming and whatnot, all sorts of cycles within cycles, Pacific decadal oscillation, the Atlantic multi-oscillation, and so forth. But what ends up happening is, if you model the controlling forcings that we're seeing human-produced greenhouse gases, it matches very well. And this is how we know we're on the right course for prediction in terms of modeling. Global temperature, the warmest years. Of course, everyone remembers the Paris Peace Accord, Paris Climate Accord, and Vietnam years, right? Anyway, so we're looking at the temperature at 1.5 degrees. That's where we wanted to not reach. And it already did that in 2016. Isn't that interesting? Why? Because we had natural variation from El Nino, which actually warmed up the planet, the Pacific Ocean, released a lot of extra heat on top of the warming that we're seeing from man-made greenhouse gases. So we actually hit 1.5 degrees Celsius, and this is where we wanted to kind of stay. I don't think it's going to be a possibility to even stay below 2 degrees the way things are headed. Even more worrisome, this is only this little red line here, land, atmosphere, and ice heating. That is what we're basically seeing right now with global warming. All that other energy is going into the ocean right now, and you can see that it's about 96% or so. So what the heck's going on? Is it a human-caused climate change playing a role? Is it us? Yes. I've had other things in there that would not be appropriate. We're going to come home a little bit, come into Vermont, take a look at some of the signals we're trying to also see. Does this match up global, planetary, or is it regional, or et cetera? So we are seeing that sort of rise in temperature. This is from one of the climate assessments, 2014, fairly recent. And what you can see is that there's the squiggling lines. There's a lot of natural variation, but you can see the general trend. The temperature is warming. And again, this is in Vermont, many lowland cooperative observers that started some of the data that goes back from 1888 to 2013. And you can see that there's a bit of warming. You can also see some interesting little variations here. So this is the Burlington, Vermont temperature from January year-round annually. And you can also see that there is that warming, but you do see that the signal is kind of up and down and whatnot. But in general, it is also showing up here in our local climate data. These are different cities. On the left-hand side, if you look at Vermont, there's one that stands out. Now, what is that? So we're talking the second one down, 1973 to 1982. You can see that the Vermont area, for whatever reason, that particular period was warmer, it kind of cooled down, and then it rose. But you kind of see the general trends, and it doesn't warm evenly everywhere. There's like minor feedbacks that kick in, either positive or negative. So you'll see minor variation in the typical microclimates that we have so many of in Vermont. Just in fact, one part of your yard is one microclimate, the other part of where you live is another microclimate, and you live very close by. So there's a lot of variation. So if we're just warming up in a natural trend, the basic linear trend, this is where Vermont will end up under the scenario of the highest emissions, RCP 8.5. And you can see that by 2070 to 2090, Vermont would be something like northern Georgia, northeast Alabama. Pretty amazing. And now the lower emission scale will take us into, I don't know, southern Ohio, West Virginia. You choose. Lake Champlain freeze-up data. This is interesting. I want you to keep your eyes on the ice. So the ice is a diamond shape here, and you see that no ice reported in some of these years, but notice as we got closer to 1952, 60, and so forth, a lot of reported diamonds there. And based on satellite imagery, a lot of this and no reported freezing. So you can see that the tendency is that we're losing ice on Lake Champlain. But there are some curveballs with that as well, and we'll get into that in a second. Spring warming, it's anything like what we saw this spring, right? We should see temperatures even running above average of 2.9 degrees. This is in Burlington, that's 1970, that's 2018. This is a very new chart, and you can kind of see where we should be in the spring. We should be having an earlier spring, not a later spring. Changes in the date of the first and the last freeze dates. So what this shows is that the last freeze date it's like through 1960, 2 to 3 degree change per decade is what we're basically showing here. So we're seeing the last freeze happening a little bit sooner, and we're seeing the first freeze happening later. And so consequently, our growing season is expanding. Vermont farmers see climate changing, Macintosh apple tree. This is kind of a proxy for their blooming, and that's a really good thing in nature. I'm also a beekeeper as a hobbyist, and I keep an eye on a lot of environmental things because I really want to plug in as much as possible. Well, these are the kinds of things we use as proxies. So this is a bloom date, and you can see 1970 to 2010, and you can see that the bloom date is happening earlier. It used to happen later, and it's happening a little bit earlier. Of course, if you extend that line, you'd see that trend continue. And as we know, this is the USDA hardy zones. The interesting thing here, this is in January 1990, and you can see that maybe up in the Northeast Kingdom, you can see a little bit of darker color here. That would be zone 3, and then mostly that blue, that's zone 4. Notice now 2015, we're basically all in the darker green now. We've moved to zone 5 and so forth. Joe's Pond ice out, same kind of thing. Everybody wants to try to know this, right? So you can see that it's happened, whoops, let's go back. All right, so you can see that this has happened, boy, in the 1st of April. There's been some really early ice outs recently, but you can see the trend here, 1985 to 2010. It's happening earlier. But beware, because I'm about to show you some curveballs. This is our annual average precipitation. This is based in 1961 through 1990. And what this shows is that under 36 inches, the Champlain Valley is relatively dry. We have the general Vermont period hole in precipitation. It really doesn't rain as much here. You go north, south, east, and west, it rains more, okay? And that kind of extends a little bit in the plain field. And then, of course, along the Connecticut River Valley. And why? Well, this is the Green Mountains. The mountains are terrain-driven. Weather systems that moisture hits that mountain, it's going to rain out a lot of that moisture, precipitate out. And that's why there's the Green Mountains, of course, along this line here, have greater than 44 inches. That's, you can see some of the local ranges like the Worcester Range, the Northfield Range, the Roxbury Range, Standard Mountains, and so forth, up in Willoughby, and so forth. So the mountain terrain, definitely the mountains create their own weather and they add much more moisture than what you're seeing down in the valleys. In those terms, thinking about annual average rainfall and then looking at the trends, 1910 to 2010. So this is 100 years of data. You see the trend here, how northeast extremes and one-day precipitation is going up. And this is what we're getting into here. And of course, higher trends in precipitation that falls all at once means flooding. Change in average annual precipitation from 1941 to 2013. You can see that 1941, 2013, you can see that trend going up. Again, this is at the Burlington International Airport, solid data. But look at this, the number of days per year with greater than 1 inch falling in a 24-hour period at the Burlington National Weather Service office at the airport. You can see that the trend is, there's a little bit of a variability, but notice what's happening recently. That is the trend of what we're seeing, heavier rainfall. That rain falls on the mountain slopes, collects into the headwater streams, collects into the bigger streams, they go into the main stem rivers and so forth. One of our main stem rivers is the Mad River. 10 more days per year with high flow conditions, from 30 to 40 days per year, a projection of 80% increase by 2100. Meaning, we're going to see a lot more water in our rivers. It's going to be a big deal. Where are Vermont's towns? They're mill towns. They're along the rivers, right? So back to greenhouse gases and a little bit of revision here, but I want to make you keep this in mind here because again, 3 million years planet hasn't seen that kind of CO2, carbon dioxide. It's way out of whack. So the Earth's temperature is starting to catch up. We know that. Now notice in this chart from 2000 to 2010, look at where the warming's taking place. You see, this is zero, no warming. Anything to the left in these colors is a cooling. There's a little bit of that in some parts of the world. You can notice little hot spots or cool spots in this particular case. But notice that the Arctic is really warming. The Arctic is warming 2 to 3 times faster, and this is where some of our curveballs are coming in quickly. The Arctic temperature record high in 2016 was 8 degrees above what it was here at 0 degree latitude. In other words, this is the equator. We're about 45 latitude, and from 70 to 90 north, excuse me, this is a little bit further to the north, but you can see that in the southern part of that 70 north latitude, you actually have a major increase. And during the months of basically August and this particular Arctic high temperature is when the ice is starting to melt very quickly. And that typically is around the 15th of September. So the air temperature anomalies for December, January, and February during that period of time, the winter, are really warming up even in the wintertime across the Arctic. And this is causing some issues. Why is it warming up? Well, extreme minimum ice extent was the last in 2012, and you could see where the ice used to be. And this is about 1980 right here. So in that amount of time in our lifespan, since 1980, we've seen that much ice get lost. And of course, the ice is thinning. There's some thicker ice that's up in the Canadian archipelago, but it is definitely vanishing very quickly. This is why it's a problem, why it's warming, because when we have ice, the albedo, the reflectivity of the ice, causes that ice to stay the same. It doesn't really heat up very quickly. But when you have open water, boom, it heats up and the water is very dark. So it pulls that energy. How unusual is this recent loss of Arctic sea ice? This is 2012. This is 1870. And this again, 2012 right here. You can see just in the most recent from 1870, from whalers and whatnot, we see that the trend here And when that Arctic sea ice melts all by itself, we call this a blue ocean event. And the projections are anywhere from 3, 4, 5 years from now to maybe 10, 15, 20 years from now. And that's when the weather's really going to get wacky, really wacky. Now, looking further back in time, you can see that the reconstructed sea ice extent, what they did is they looked at the seafloor of the Arctic Ocean, and when they had no ice, they had miniforma, these little creatures, little crustaceans at the bottom of the seafloor. So consequently, they could figure out and reconstruct when they had changes in the sea ice because of the sunlight that shines through it. Well, that's 2012. So you go back to that time period, we're talking 2,000 years here, reconstruction going backwards. That's where we are right now. So this is a major, 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 major change to the planet. As of right now, this is where our sea ice is. So this is 2019. As we have winter, the sea ice gathers, it thickens. There's more extent. It's cold up there. There's no sunlight, right? So now we get into, say, late February and March, we should see a melting, and that's the natural curve. This is 1 to 2 standard deviations. This is 2012, and that was the track it took, and it kind of detoured here after May. But you can see where we are here in 2019. So the chances are pretty good. We're probably going to either see some sea ice. The 2019 might be the record minimum sea ice, but it's going to be close because you can see that trajectory. If that were to stay the same, 2012 would stand and probably keep it as number 1. But needless to say, we're starting from a very precarious situation here. Near surface air temperatures in the fall, well, this is the mid-latitudes, and that's us. We're about 44.6 something north right here in Montpelier, and 45 north is halfway between the equator and the pole. So at mid-latitude, this is our temperature trend, that being 0. Everything above that would be above, and everything below that would be negative numbers, obviously. But look what the Arctic's doing compared to what we're doing here, and especially roughly about 1995. That's when things started to really kick in and we started to lose a lot of sea ice. And they call this Arctic amplification. So Arctic amplification is strongest in the fall because of the sea ice loss. This is looking down at the northern polar region. You can kind of see the United States, that's Alaska. You see Florida, Mexico, and so forth. Well, it's causing strange pieces, strange vortices, if you will. The polar vortex, or the spinning of the planet, winds at the North Pole, the northern hemisphere, it used to be a lot more circular, not perfectly, and there's always these troughs and waves and whatnot, but what's happening is we're seeing a change in the pattern. What's happening is 1,000 to 500 millibar thicknesses, say roughly the ground here, to about 18,000 feet and higher, is causing some major changes that are taking place. They're actually increasing ridges or areas of higher pressure that then cause a little bit of the warming. And so that's some of the mechanics of what's been taking place in the Arctic, but it's a lot more complicated than that. And what that does is it causes a weaker polarward gradient, meaning the difference between the equator and the North Pole is now less. Why? Because the Arctic is heating up. The equator is not heating up as fast. So the Arctic's trying to match the equator, oddly. And what this does is you consider a layer of the atmosphere stretching from the warm area here near the equator, let's say, and to a cold North Pole, polar region. And you can see that the thickness is a lot shallower here. High thickness, low thickness. That cold in the Arctic is the way it's been for millennia, right? Because the warm air expands, the layer will be thicker than it is in the Arctic. But what ends up happening is that the warming of the planet is causing this. Whoops, right here. So what you end up seeing is this, there's not as much difference. And what that does is it causes the Arctic warming has a tendency to weaken the jet stream. And that's really what's going on. And that weakened jet stream, the wiggles in the jet stream are really where it's all at right now and what's going to be affecting us and throwing curveballs into the natural linear progression of this warming that we're seeing. So as the high latitudes warm faster than the middle latitudes, this is October, November, December, when the ice is at its thinnest or has melted out a little bit. Where we're correlating here very nicely is the sea ice with a measurement of the zonal jet stream winds. And you see that they go pretty close hand in hand here. And a lot of this work is done by Jennifer Francis again. So it's about a 10% difference, but that 10% difference is actually bigger than that for like 45 north latitude, where we are here. So Rossby theory, the weaker the westerly flow favors more meandering patterns, slower eastward wave propagation. This is a river. Think of the river of the Winooski, for example, between, let's say, East Montpelier or Plainfield to about the lower part of Marshfield. The river, where it flattens out and it moves slowly, starts to do these big wiggles, just like what we're seeing right here. Well, the air does the same thing. It's part of physics. It's fluid dynamics. High amplitude meandering rivers of air mimic slow moving rivers of water. It's the same kind of phenomenon. So the effects of Arctic amplification cause the weaker westerly winds when the polar vortex is strong. When it's weak, it basically allows those troughs and weird polar vortices, sort of what we call daughter vortices, to sort of develop. And some of those can become nor'easters. You've heard about the polar vortex and all this. The polar vortex is a hard thing to actually explain. It basically is at the pole. It's called the circumpolar vortex, for one thing. The media has totally disgracefully ruined it. But the polar vortex is just basically where the air is spinning around the northern hemisphere. There's a stratospheric component to it and a tropospheric component to it. Where we live here and where our weather is in the troposphere. What ends up happening is in the high latitudes, you have these big waves because of this weaker flow, this weaker jet stream. This is the work, again, done by Jennifer Francis. And what's happening is the ridges are getting bigger. And that means the troughs downstream are getting bigger. So the westerly winds are coming across the Pacific. They're not doing this thing anymore, what we call it zonal, going from west to east. They're ridging up and then troughing down. And these things can sometimes get stuck. This is the wavy jet stream. This is a real jet stream animation NASA did probably a few years ago. And it's a repeat and loops over and over. But you can see how this East Coast trough here is getting stuck. Well, that's where you have severe weather. Why? Because on one side of that trough, you're getting moisture pulled up north, and that's spinning up low pressure, surface low pressure, like nor'easters. You get heavy rain, flooding, or heavy snow, or high winds. Meanwhile, the people under the ridge, all they're seeing is bright sunny days and no rain. What do they get? Drought. So they're getting the opposite effect. So these weather patterns, due to this waviness, because of the Arctic sea ice loss, relates to the waviness of these jet streams and them getting stuck. And that's what's related to our extreme weather. More intense ridges. So this, again, some work done here. Extra heating intensifies the ridge, making it more persistent. And you can see how that goes north, and there's no ice there north of Alaska, how it is right now, actually. And so the ridge is more intense. And what does that do? It drives a downstream trough. What do you think is happening right now? It causes extreme weather. Boston in February 2015, big cold blob, big ridge of higher pressure up here. You can almost see where the jet stream came down. Boom, just like that. Big ridge over the Atlantic, big ridge on the western seacoast there. Causes drought, they don't get any rain, we get everything. Comes through Vermont, everything comes through Vermont, right? So it affects us as well, these big changes in the sort of the weather systems at large, the overall flow of, at 18,000 feet, 500 millibars. And we get wind damage, we get severe thunderstorms, we get flooding. There will be a time that we'll be under a ridge at some point, and we'll wonder, when is it going to rain? When is it going to snow? And it could stay dry, and we could see massive forest fires. We're not immune to that. It's happened in the past. It'll happen again, and we could have massive forest fires. Now, if you're like me, I have trees growing next to my house everywhere. I live out in the woods. That's my preference. But what if those trees are starting to start getting disease-ridden like they do out west with bark beetles and whatnot, and all of a sudden they become super fire-prone? Could happen. But we get this kind of thing, and even it affects low-income Vermonters, it affects low-income people, but it also affects high-income people as well, because you basically can't run, you can't hide. This is the insurance company this is Munich Re, and I want you to study this just a little bit, if you don't mind. So this is meteorological events, tropical storms, extratropical storms, like a nor'easter in the summer, let's say, a wet nor'easter, convective thunderstorms, squall lines, and local high winds and this kind of thing. That's in the green. The next is the hydrological events, meaning water, obviously our rivers, our streams, flooding, having to do with rainfall, precipitation, and then climatological events like extreme temperatures, heat waves and droughts, forest fires and whatnot. You see the trend here. This is Munich Re. Again, they insure all the other insurance companies around the world, and they're one of them, I believe. There's a few of them. I'm not sure about that, but you can see that the trends are increasing, and they really know it because they have to pay out of pocket. Nature's carbon tax. 2018, billion-dollar disasters. You can see that the worst was 2011, second 2017, 2016, 2018. 2011 was huge for us. Obviously, we had Hurricane Irene, and then we had the May 26, 27 thunderstorm training that caused all the trouble here in Montpelier, and Barrie, and Waterbury, and so forth. So this idea that you're not going to get taxed is baloney. Top climate hazards in 2050. This is a projection. So we're looking at precipitation. This is flooding and so forth. Notice that, storms, probably tropical storms, hurricanes and so forth. And then you got sea level rise along the coastal areas. You can kind of see what's going on here. Drought potentially in the Ohio Valley, certainly out west. And then you got the blue water deficits that kind of go hand in hand, I guess. So this is kind of interesting. It's a little bit hard to explain, but when the polar vortex, basically in the stratosphere, starts to heat up, we call this a sudden warming situation. It's a sudden stratospheric warming event, SSWE, and in the terminology here. So when that happens, it basically weakens the polar vortex down below, the tropospheric polar vortex, and that's how we get these daughter vortices, and that's when our weather really goes wild, and we get these big swinging troughs and all this. And it's kind of still happening right now out over the West Coast. This is definitely developed. This is new science data. So what they've done is they've correlated, that's when all the extreme weather is happening. And they've looked across the world, the Northern Hemisphere anyway, and they've been able to correlate this, this warming, the Arctic cap. Taking emerging mechanisms, and this is kind of what we had this winter. This is kind of new science. It's pretty interesting. And so I'm going to stop for a second and just say that, remember all those trends I showed you of the temperature warming linearly, okay? There's obviously going to be some waves in there. But now we got new curveballs that are coming in that haven't really been factored into the IPCC yet, in my opinion. And the IPCC, the Intergovernmental Panel on Climate Change, is a very conservative body. They have to have everybody in their science team, thousands of people all over the world, sign off on it. If one person disagrees and says, no, that's too strong, they have to water it down. And that's what comes out. It's a watered down I was going to say a piece of something, but I'm not going to say it. It's not useful when it's watered down because things are going faster. But when we have this kind of warming, this is December, January, February, and this happens to be where the warming's been taking place, right here in this particular Cohen is Judah Cohen out of MIT. And in 2014, what he found is that basically this warming in the Arctic now comes vertical. It sends up a sort of a wave flux that goes into the stratosphere. And it starts with the loss of Arctic sea ice, which then causes an area of higher pressure. The area of higher pressure causes a kink. You can kind of see it here, and then it develops a trough downstream over Siberia. That whole action begins to work into the stratosphere, and then the stratosphere works it back down. So there's like step 1, step 2, step 3. The net effect here is you see how these curvy troughs, just like we were showing, that causes all the extreme weather? Well, that's exactly what happened this year, and it is actually still happening right now. We've had a sudden stratospheric warming event with the polar cap heights actually very, very warm aloft over, geez, it started, I think, in January, then it kind of lingered into February, then it went away for a little while, and then in March and April it returned, and it's odd to see that, but it has everything to do with Arctic sea ice. Again, that's one of the contributors, the main contributor. So earlier snowfall along the most coastal areas promotes a trough. Wave energy transfers to the stratosphere. The polar vortex weakens. You get a wavier jet stream, and that's where you get cold continents and warm oceans. And when you have cold continents next to warm oceans, you have extremely strong baroclinicity, meaning the temperatures, those temperature differentials, those temperature extremes next to each other spin up barometric pressure changes, namely storms or low pressure systems. So, looking at March the 1st, 2019, anybody know what this is? Lake Champlain. It was totally 100% iced over. Remember all those diamonds I showed you? How the trend is that we're seeing less and less ice? Well, polar ice loss is having an effect in a wavier jet stream. It also caused a sudden stratospheric warming event that then boomeranged back down, and it caused a colder than normal winter, especially the last part of the winter. And that is the effect. So it's the evidence, again, it's the same thing I just showed you, and it is just now, this is very, very new science in the last 5 to 10 years, and it looks like this year is a good example for it. And so there'll be a lot more information coming out in the future. What did it do? Well, this is Mount Mansfield's average snow depth at the stake. You can see where we started out early. We had some pretty good storms, a little bit of melting, and tremendous amounts of snow on top of Mount Mansfield this year. And you can see where we ended up, and I think it was still higher than that. I think it was around 114 inches on the level at the stake. I believe that might have been the maximum. So Arctic amplification is alive and well. The high latitudes are warming much faster than the mid latitudes, especially in the fall and winter. You have the poleward thicknesses, the gradient is weakening a little bit. That's causing the jet stream flow to weaken at 500 millibars. Peaks and ridges are elongating northward. You're getting that slower flow, so you're getting that big wiggle, that sort of snaking, if you will. And more amplified Rossby waves should progress eastward more slowly, and that's exactly what they're doing. That causes severe weather, too much of one thing. Weather conditions more persistent, increased probability of extremes, cold spells, heat waves, flooding, prolonged snowfall, and drought, all at the same time in different parts of the world. Here are some examples. Note the big trough of low pressure right here. Note the big ridge of higher pressure. This is when we had the 2012 heat wave. Does anybody remember that? In March, we had temperatures in the 80s and almost near 90. Crazy stuff, right? What is it caused by? These kinds of weather systems. You can blame it on the loss of sea Arctic ice. Arctic sea ice, excuse me. January 6, 2014, we heard this is when the media went crazy with the word polar vortex. They, every time it got cold, oh my God, it was the polar vortex. Well, in a sense, it did break off it should be up here, right? So a daughter vortex broke off, and why? Because we weakened the polar vortex. The polar vortex went missing. And so these other, at 45 north latitude, the mid latitudes, that's when the other things happen, and that's when we get our severe weather. So this is something to contemplate. So as we're heating up the oceans, we're pumping in a lot of heat due to carbon dioxide raised. We're also adding about 6% to 7% a year of more moisture, because as the temperature warms, it's a product of physics. You're adding more moisture. More moisture can be held in a warmer temperature. So you're having bigger raindrops. You're having more juiced up storms. So that's going on. If the temperature is below 32 degrees, it's going to fall as crystallized snow. What does that mean? That means our snowstorms could be way bigger. How would that be? Let's think about this. So let's say if we get a 150-year storm or a 200-year storm of I don't know, 10 feet, it's possible if we get a stuck weather pattern. So that puts us in a sweet spot in a sense, especially in those years that we have the trough of lower pressure that's right over us. Doesn't always work like that. Some years it's West Coast, some years it's East Coast. Sometimes it's over Eurasia, and we don't really have a whole lot going on in North America. Last couple of years, it's been all about North America. Here's some examples. I showed you March 2012. That was when we had the 80 to 90 degree temperatures in Burlington. People were at North Beach in the sun in March. Think about that. Think about this May. What kind of craziness, right? Winter 2012, 2014. Look at the differences here. Cold versus warm. These are the variables that we're seeing. Why? Cold trough, warm ridge. Reverse, warm ridge, cold trough. 1 year might be that way, 1 year might be that way. You see what I'm saying? Can you predict it? Not yet. We're working on it, but Arctic sea ice, that's the key. Was the path of Sandy affected by record sea ice loss in 2012? We had a big ridge of higher pressure. Notice the big trough of low pressure. All of a sudden we have tropical storm, Hurricane Sandy coming up the coast, doing its typical thing. They start off Africa and work the way in the warm water region there and become asymmetric and basically come up the East Coast and get turned typically by the jet stream, except that didn't happen. It turned to the left. Why did it turn to the left? Well, guess what? The Arctic was much warmer than normal. We had, look at this weather pattern. Look at how squirrely these are here. That was during Sandy. That's when we had that Arctic, that blocking ridge of higher pressure. The storm, the tropical storm coming up the coast got blocked, had nowhere to go. So it turned left into New Jersey. So as the oceans warm, hurricane seasons are lengthening. The storms can survive further north and perhaps interact more frequently with jet stream troughs. And you get these kind of results, Sandys. This is another example I threw in here. This is fairly recent, January, March 2015. This is when we had, let's see, January through March 2015, and that's 2016. Okay, that's a year before the big El Nino. This is El Nino. You see that warmer temperature right along the equator there off South America? It's kind of hard to see, but this is North America, that's Florida, and it kind of goes up there, and there's the North Atlantic warming hole. And there it is again. That's almost a permanent feature, by the way, now. Something to consider, and I could do a whole nother talk on that alone. But it basically, look at the difference. Much colder across the eastern half. 1 year later, El Nino kicked in. Look at how warm it was. Remember how warm it was? It was that warm. And that was Christmas Day. Christmas Day. And there was no snow on top of Mount Mansfield at the stake on Christmas Day, December 25th, 2015. That's what it looked like at that moment. So fast forward, I guess, to what's going on currently. 925 millibar, that's about 2,000 feet off surface. This is the temperature anomaly looking down on the North Pole. You're looking from the top of the globe downward. And what you see here, this is Greenland right here, the Davis Straits, Fram Straits. This is part of Russia, and you can kind of see Alaska right here as well, the Bering Strait. Well, the real warming has been taking place sort of a little bit offset on the North American side of the Arctic, if you will. And that's what it's been doing to the jet stream. So the jet stream has a giant ridge of higher pressure that goes through Alaska. This is the current setup, or at least last week. Then it basically comes all the way down the coast, digs a gigantic trough of lower pressure. They're getting, it's almost June, and they're getting snow like crazy in Colorado and all the way to the Sierra Nevada and the upper elevations of the West Coast, the Western interior. Meanwhile, all that jet stream energy interacts with moisture coming in off the Gulf of Mexico. Day after day after day after day, stuck weather pattern, day after day of tornadic supercell thunderstorms, right? What do you think that does? Do any of you eat any food? Tornadoes. Look at the counts here. Just blows the records away, blows them away, the amount of frequency of tornadoes. They had 500 this May, and since the first of the year, 1,000 tornadoes were cataloged. Why? Loss of sea ice in the Arctic Ocean, causing a jet stream to slow down, to stall over the same area, pump the same conditions over one particular area, cause the environmental factors to produce supercell tornadoes, which also rain out very heavy rainfall time after time after time. Stuck weather patterns. This is going to be this weekend, speaking of another stuck weather pattern. This is Pakistan. They're going to be 122 degrees. They're a poor nation. A lot of them don't have air conditioning. A lot of people die due to heat waves. This is happening this weekend. And I thought I'd leave you with this. This is the summer forecast, and two ways of looking at it. This is Judah Cohen, who developed that stratospheric sudden warming event that then translates down into the troposphere and weakens the polar jet stream. It causes the wavy aspect of the jet stream and so forth. Well, that's his forecast. That's their computer modeling, which indicates basically a warmer than normal summer. How about that? The European model, very trusty, kind of near normal, but it's warm in the Arctic still, but it's cold in the Central Plains. Kind of a continuation of this whole pattern, but not as amplified. And I believe that is it. Thank you very much.
Hello. If people have questions on cards, if they could hand them to Elizabeth, who's picking it up right now, we appreciate it. Roger, we're going to start with this. I think you answered it, but I'm going to see. Do you continue to think that Vermont will be in the sweet spot of climate change, not too hot, not too dry?
Well, I think it's probably a whole lot safer to have heavier rainfall than no rain at all for life. Water sustains life. You can grow food with water, you can't without. So in that sense, and that also probably means climate refugees. I would not be surprised in the course of the next decade, 2 decades, to see mass migration into places like Vermont. And I don't know if our planning is gonna, I mean, this is on the fly because things are changing so fast. But in a way, we are in the sweet spot, but there are ramifications. If you live in a floodplain or you live in the new floodplain, which could be 1,000-year floods every spring, could be problematic. And this is what's going to be. It's water, 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 water. And that's the deal.
What suggestions do you have for the average Vermonter to reduce the negative impact of climate change that's coming to us?
So just to reiterate, so what should they do? Is that what you're asking? Or
Yeah, what suggestions do you have?
Suggestions.
I'm just reading.
Boy, I don't know where to start. On a political vein, we need to have our leaders really start working for its citizenry and not ignoring the subject. That's one, that right off the bat. I would also say, I'm just going to add to that, everybody can do their part. I think a lot of us here in Vermont are trying to do the right thing. I think Vermonters, over the past maybe decade, has kind of lost a little bit of its zeitgeist in terms of leadership, but we could get it back by being a model, a role player for the rest of the country, especially the stupid South.
All right, this one, we'll see. I've lived in Vermont for 70 years, Windsor County native. Have noticed that Vermont has less snow, not now, but more wind. What accounts for that? So maybe Windsor has a different aspect than Mount Mansfield.
Okay, so it's a little bit of a, I showed you some contradictions, right? So if we were warming in the 90s, the 80s, 90s, and into the 2000s, and all of a sudden the sea ice loss started changing things up. So there's that kind of feedback going on. There's the natural warming feedback that's going on. So there may be years that have very little snow, but there may be years that have tremendous snows, not anything like we've ever seen in our lifetimes. And that's the kind of extremes and variability we're going to start to see.
I hear a lot about invasive species. Is it smarter to spend money stopping them or develop ideas to coexist with them?
I'm sorry, I couldn't hear the echo. Say that again.
I hear a lot about invasive species, but is it smarter to spend money stopping them or develop ideas to coexist with them?
Above my pay grade, I hate to say. Invasive species are going to come with the climate, and the climate's going to change naturally. The whole thing about climate change is not that the atmosphere and the climate is changing. It's the speed at which it's changing. It's the speed that ecosystems cannot catch up. It's the speed of the change involved. You got to understand, we're blowing through geologic time right every year. Every decade is just blowing through geological time, that it hasn't changed this fast, and it takes sometimes 1,000 years to change this fast. If you look at the glacial and interglacial, all the past, the Younger Dryas, the Eocene thermal maximums, these things take a long time. The kind of scale and speed that we're doing it, nothing is going to be able to catch up, and that's a problem, and it's happening very quickly.
Okay, one close to my heart. What are the probabilities of heavy valley flooding like in downtown Montpelier?
So the first part of the question, I'm sorry, I'm a drummer, and I'm a little deaf sometimes, so I'm sorry.
All right. Probabilities of heavy valley flooding around here, especially downtown Montpelier.
I think we'll be having a FEMA grant every summer.
That's simple.
We're going to have a lot of floods. A lot of floods. It's going to, and what they're seeing in many locations, many locations, you're seeing, 3 months worth of rainfall fall in 2 hours. This is happening all over the world.
From this person, it's been my understanding that Vermont's temperate climate comes from warming of the Gulf Stream. I believe the Gulf Stream is part of the Salt-Haley ocean currents. What will happen to Vermont's climate if the Gulf Stream changes extensively or stops?
Interestingly, we're warming up if the Gulf Stream stops, all the warmth that's going, I used to work at the National Weather Service office at Cape Hatteras, North Carolina, and the Outer Banks there, you're closest to the Gulf Stream, right off the coast before it makes its right turn sort of out to sea. And we call that the headwaters of the Gulf Stream. And there's these weird curly cues. I used to have to plot all this stuff, and it was a real pain. But so I knew where the headwaters of the Gulf Stream were, and these little sort of perturbations, little vortices even in the ocean currents. And now what's happening is because the Gulf Stream is slowing, the thermal haline circulation is basically, the Gulf Stream is backing up. And so it's going much further north. It's going right off Long Island, right off Nantucket. Occasionally, some of it actually comes into the Gulf of Maine now, and that's a real problem for a lot of cold water species of crustaceans and fish and whatnot, and it could be real economic disaster in the near future for that. So there's a lot of changes going on with the Gulf Stream as well. It's going to warm up on this side, but what it's going to do is it's also going to cool down in the North Atlantic. You saw that North Atlantic warming hole. That could expand to Europe. It could cause northern parts of Europe, Scandinavia, UK, France, and East to be much colder on a regional scale, all due to global warming. It's crazy.
Okay, we've got time for a couple more.
Yep.
How would heavy volcanic activity affect our temperature? I'm thinking of a large ejection of ash.
Yes, okay, so there's two types, there's many types of volcanic ash and whatnot, but you need a stratospheric type of ejection, and the kind of Mount Pinatubo or El Chichon, or you think of Krakatoa or Mount Tambora, the year without a summer here in Vermont, 1816, froze to death. That was all related to the filter or the aerosol effects of the blocking of the sunlight. And if we were to have volcanic action, stratospheric volcanic action that has to eject a lot of material into the stratosphere, it can't just be 20,000 feet like Mauna Loa or some of the smaller volcanoes. They're not small, but they don't really pump that stuff up really high into the stratosphere. It has to get above the tropopause. When it does, it stays up there for a long time because it can't rain out because all the weather's down below it. So in a Pinatubo type volcanic eruption, you'd have 2 years of cooling, but it would be just temporary. And what it would do is mask the warming. And at the same time, when you mask the warming, certain people in politics will want to use that against global warming.
Sort of the follow on that is sulfur dioxide used in geoengineering.
I've read up on this stuff, and to me, this is a little bit of a Frankenstein kind of deal. If you start playing, there's other ways of doing stuff, but I think we're going to have geoengineering, but not the kind of deal where they're going to pump sulfuric acid into the stratosphere. I think this is a little dangerous, and a lot of people think it's very dangerous because, you know, it's a sensitive item, shall we say. There is a lot of other stuff coming online that could be machines that actually suck CO2 out of the atmosphere. There's a Swiss company, there's a few others, I think, and these have more promise in the near future. But my God, we have to get off fossil fuels. We got to stop the source, and then start cleaning up. You spill this idea that you kick over a carton of milk and you run over to get a sponge, and while it's, you know, pouring out across the table without picking the carton of milk and stopping the source. I don't know how people are thinking this way, and obviously we know why they're thinking this way. It all has to do with money, and our system is corrupt.
So as the last question, I think this person's channeling my wife. Where in the world would you live if you didn't live in Vermont for the best weather, perfect weather, if that is possible?
Boy, it depends if you like the tropics or what. If you see, I've heard most recently that Central America and all the tropical areas will be uninhabitable. It's just too hot. I think it's 38 degrees Celsius. If you have dew point wet bulb temperature at 38 degrees Celsius, you cannot, the body will not sufficiently cool itself because there's no sweating anymore. That it's just too hot. And they've reached that already in parts of Iran and I think Pakistan, and it's killed people. So the tropics are going to get warmer. It's going to get warmer more slowly. What's getting warmer faster, obviously, is the North and South Pole. So that's where probably life is going to end up, you know, toward 2100, maybe, maybe not. Now, just to speak a little bit about this, there's a lot of folks who think that we only have a couple years left. They think that methane tipping point could kick in, and that's it. Lights out. We will be, we're done. Those are the more outlier. Most people think that this is probably good for another 20, 30, 40, 50 years, much past 50, 60, 70 years. Unless we get off the dime this decade, forget about it. It's Venus, we're runaway to Venus. But we have choices to make, and we can react fast if we want to. We built a nuclear bomb in World War II. We can do these things. We can do a Manhattan Project. I just don't see the will yet because the weather is not quite beating up people to the point, it's starting to, but I think the weather billboard will be the whole key here. And our politicians, it's not just our politicians, it's us collectively will have to adapt and mitigate a warming world that will be with us the rest of our lives.
Thank you, sir. Now we're going to try and shift for a moment because, well, that's a harsh place to leave. So let's talk a second about a better idea on how our upend in climate might be reached in the future. Tonight's talk took us all out of our comfort zone and closer to understanding how we're going to need to action to get together through this. Of course, such truth can be overwhelming and leaves us asking, well, what can I do? I personally believe we can do a lot to adapt, and so that the worst of the effects can be managed locally, but to do that, we're going to have to do it together in community. Looking out at our nice audience, I'm reminded of what an amazing community we have here in Montpelier. Our collective future well-being is going to be dependent on that community coming together to face these challenges. The first step is to understand the difference between mitigation and adaptation. For climate mitigation means all those efforts to cut down CO2, which are absolutely necessary. You know, drive an electric car, use solar power. And as of the Department of Energy today, we now have to, for those of us on the other side, fight against molecules of freedom. That's what oil is now to be called in the future. What we need to keep in mind, as Roger noted, that even if we stop putting greenhouse gases in the air today, we'd still have 30 years of hard effects and increased disruption just from what's there today. So that brings us to adaptation. Goodbye. Adaptation requires admitting the changes are coming and working to prepare ourselves and our local environment to meet them. Of course, anything done in this regard will also reduce our carbon footprints, but our efforts must also help to protect our community's future. So we created Sustainable Montpelier Coalition a couple of years ago to mobilize that response. Well, we need everybody to be involved, and that's where we are now. So Roger, close to the end of his talk, started talking about food with the big floods over Oklahoma and all the farms. It's pretty obvious to me, and of course anyone who farms and gardens right now, this year is really the mud pits. Roger just showed us what the Midwest looks like. Imagine what that's going to do to our food prices later this year. But maybe it's past time that we figure out how to ramp up local production of stuff that does grow well here and insulate ourselves a bit from market variations. I'll call it the market shock. Nobody's been talking a lot about food systems recently, but maybe it's time. It's time to start asking hard questions and seeing what we can really do to create food security. Should our lawns be transferred into gardens? Should we really start supporting our local farmers, not only in farmers market, but in actually making them healthy and prosperous because they will feed us. And then there's housing. I believe that we'll be seeing a lot of older people discovering that aging in place on their hillside homesteads is a lot harder than they thought. Every time the roads wash out and the power disappears, their country lifestyle becomes more challenging. I'm meeting an awful lot of folks, I mean a lot, who would like to move to town but can't find anything affordable. In fact, actually, they can't find anything at all. And the situation means that we need a lot more housing soon. As much as I appreciate the 50 units that Downstreet has built downtown, the size of the Vermont Back to the Landers community who came here in the 70s, 80s, is hundreds and hundreds just in surrounding towns. Denser downtown living is more energy efficient and convenient. So how is our community going to help create them, stay in this community as things get more challenging? Now, you remember that design competition we did a couple of years ago, which got us started? We had a lot of interesting ideas presented on how to fill the easily buildable lots downtown. Now, of course, most of those lots are sitting under parking lots, so it makes it a little bit of a challenge. And to do that, we're going to have to start creating other ways of getting around town that are both convenient and affordable. We've been working with the state, Sustainable Montpelier has been working with the state to develop what's called on-demand microtransit. And you'll be hearing a lot about that in a few months, and we're hoping that a year from now we'll actually see something starting to happen. And that is going to be a first step in creating a post-car future here. But we really need people who are interested in this to start joining together to talking about what else is needed. It's been sort of out there like, oh, well, that's just reality, we can't touch it. No, it's time now to start touching it. And we can start asking the same questions of the demands on our water and sewage system from all of the rain that's going to be here. I think we clearly saw that. It's really important how to consider the role of the rivers in our future. Flooding and sewage overflows are continuing as a big issue, and they're going to get worse. But who's going to be the voice of our rivers? How are we going to be involved in making sure that we can mitigate and slow down the storm surges? Perhaps we could ask the city to declare a climate emergency and that we need to start responding with a public policy that there is an emergency. Perhaps you don't know, but recently 2 countries, England and Ireland, have declared climate emergencies. And here in the US, 14 cities have done the same. And I could go on, you get the idea. There's a lot to do and not a lot of time to do it in. We need people willing to come together and grapple with adaptation challenges that we're going to be facing soon. Now, we'd like to hear from you as to what you think is needed and what you think can be done. Your imagination, energy, and goodwill are going to be needed if we're going to address the mounting challenges. That's why we handed out those comment and commitment cards as you came in. We'd really appreciate it if you could take a couple of minutes and just think about this and fill those in. We'll collect them as you're leaving the building, but some of you may have public questions and comments. So if you do, if you could line up over there in a couple of minutes, and we'll try and have a short discussion because I know it's getting late. But like I said, Sustainable Montpelier would really like to hear from you because it's only in community that we actually can make change happen. Thank you very much.